Hello, curious minds. What if we could build a bridge from Earth all the way to space? No rockets, no fuel, just an elevator climbing 36,000 kilometers into the sky. Sound impossible? Maybe not. Imagine this. Instead of launching a rocket to space, you step into an elevator. No blast-off, no turbulence, just a smooth, silent climb, all the way to orbit. That's the basic idea behind a space elevator. A massive structure that stretches from Earth's surface to space. But it's not science fiction. At least, not entirely. Here's how it works. The core of the space elevator is a super strong tether, anchored to Earth at the equator and extending up to geostationary orbit. We'll talk about this later. At the other end of the tether, a massive counterweight in space keeping the line taut through centrifugal force, just like a stone at the end of a spinning sling. Robotic climbers would slowly ascend this tether, carrying cargo, and maybe even people, into space, using solar power or laser energy beamed from the ground. It sounds futuristic, and it is, but the science is rooted in real physics. The challenge? Materials strong enough to survive the journey. But if we solve that, we're talking about a revolution in how we reach the stars. Okay, so building a giant elevator to space sounds cool, but how would it actually work? The key is something we talked about earlier called geostationary orbit. That's a special sweet spot about 36,000 kilometers or 22,400 miles above Earth. At that altitude, satellites orbit the planet once every 24 hours, the same rate Earth rotates, so from our point of view down here they appear to hover in place. Now picture anchoring one end of a super strong cable to the ground at the equator, and the other end to a counterweight beyond geostationary orbit. The result? A perfectly balanced, tensioned tether, a literal line from Earth to space. Gravity pulls the tether down. Centrifugal force, caused by Earth's rotation, pulls it outward. Get the balance right, and the tether stays taut and stable. Along that tether, robotic climbers could move up and down. But there's a catch. The cable has to be made from a material strong enough to support its own weight over tens of thousands of kilometers. Steel won't cut it. Even the strongest materials we commonly use today would collapse under the stress. That's where materials like carbon nanotubes and graphene come in. They're ultra-light and insanely strong. But we're still figuring out how to manufacture them at the scale we'd need. So, scientifically, it's sound. The physics works, but the challenge is engineering, especially the materials. Let's start with the biggest challenge, the tether. It needs to be about 100,000 kilometers or 62,000 miles long. But wait, isn't geostationary orbit only 36,000 kilometers up? Why go farther? Here's why. To keep the tether under constant tension, we need a massive counterweight beyond that orbit, farther from Earth, where centrifugal force is even stronger. That outward pull is what balances the system and keeps the tether stretched tight. Without that extra length, the whole structure would collapse inward. The full tether has to go well past geostationary orbit to stay stable and functional. So, 100,000 kilometers? That's longer than any structure humanity has ever built. By far. To survive the stress of its own weight and the harsh conditions of space, the tether must be made from a material with nearly unimaginable strength. Carbon nanotubes and graphene are strong enough in theory, but right now, we can't manufacture them in the quantities or lengths required. And then there's Earth's atmosphere. The tether would pass through storms, winds, lightning, and even space debris. We'd need to engineer defenses against constant wear, weatherproof coatings, electromagnetic shielding, maybe even active repairs by drones or robots. Then, there's the anchor point on Earth. It has to be placed right on the equator, and somewhere politically and geologically stable. Ocean-based platforms have even been proposed, just to avoid tectonic threats and shifting ground. And don't forget the counterweight. It must be massive and positioned precisely beyond geostationary orbit to keep the entire system in tension. Otherwise, it all comes crashing down. Powering the climbers is another puzzle. Options include solar arrays, power cables, or lasers beaming energy from Earth. But each method has huge engineering and safety challenges. In short, every part of this project would push the limits of what we can build, from materials to robotics to orbital mechanics. But that's what makes it exciting. Solving these challenges wouldn't just make a space elevator possible, it would push technology across dozens of fields forward at once. So, after all those challenges, why even try to build a space elevator? What's the payoff? In a word, revolutionary. Right now, sending anything into orbit is insanely expensive, up to $10,000 per kilogram, depending on the rocket. A space elevator could cut that cost to just a few $100s, or less. That's not just cheaper, it's a total game changer. It could open space to countries, companies, and even individuals who could never afford to get there before. Suddenly, launching satellites becomes routine. Building space stations, lunar habitats, and even Mars missions gets way easier. And because it runs on electricity, not rocket fuel, it's dramatically cleaner and safer. No explosions, no massive carbon emissions. Even the launch schedule becomes more flexible. Climbers could operate daily, or even hourly, like freight elevators for space. This also unlocks one of the biggest dreams in space exploration, building massive structures in orbit. Things too big or fragile to survive a rocket launch, like giant telescopes, space habitats, or even solar power stations, could be built piece by piece, shipped up safely and cheaply. And it's not just about going up. With a tether that long, we could also use it as a slingshot, launching spacecraft deeper into the solar system using almost no fuel. That's why, despite the challenges, scientists and engineers keep coming back to the same idea. If we can build it, it changes everything. Cheaper, safer, more sustainable, and vastly more ambitious. The space elevator wouldn't just improve space access. It could completely redefine what's possible in space. So, who's actually trying to turn this dream into reality? While no one's building a full-scale space elevator yet, there are scientists, startups, and even space agencies taking it seriously. Japan has been one of the most consistent voices. A company called Obayashi Corporation proposed building a space elevator by the year 2050. And they've already begun early research and small-scale tests. Meanwhile, researchers at universities like Keio University in Japan and the International Space Elevator Consortium are exploring everything from tether materials to orbital dynamics. NASA has looked into it too. They've even hosted design challenges, offering prizes for breakthroughs in climber tech and tether strength. Private companies and startups like Liftport in the US are aiming smaller at first, planning elevators on the moon, where gravity is weaker and the materials don't need to be quite as strong. It's not just one team or country, this is a global puzzle. And every piece of progress brings us one step closer. Will it happen in our lifetime? That depends on breakthroughs and funding. But one thing's clear, the race has already begun. Is the space elevator a dream or destiny? It's a hot debate, but for now, it's still a dream. But it's a dream rooted in real physics, powered by advancing technology, and driven by the timeless human urge to reach higher. We don't have the materials yet. The costs are enormous. The engineering is complex, but every generation has faced the impossible, until someone made it real. The steam engine, the airplane, the moon landing. Each one began as a crazy idea, until it changed the world. Plus, the pursuit itself could lead to incredible spin-off technologies. The space elevator dares us to rethink what's possible, not just for science, but for humanity. It's not just a way to space. It's a step toward a civilization that thinks in decades, builds for centuries, and dreams in light years. So, could a space elevator really change everything we know about space travel? Or is it just science fiction dressed in science? Drop your ideas in the comments. We'd love to hear them. And if you're hungry for more cosmic concepts, don't forget to like, subscribe, and hit that notification bell to keep exploring with us. Thanks for watching. Until next time, keep looking up.